Welcome to the Cosmic Pie Podcast. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
Welcome to Episode 7, Season 4 of the Cosmic Pie.
Lucky number 7. Woo!
Lucky number 7.
Except it won't be so lucky for us.
Why, you're thinking about tomorrow's weather?
I'm thinking about the weather tonight and tomorrow.
Yeah, we were doing really well the last couple of weeks. Yeah. Really mild temperature, spring.
40s.
Seemed like it had sprung.
Yeah, now.
We're going to get, 8 inches of snow possibly on Wednesday?
Something like that. Yeah, it's some crazy amount like that. And temperatures back down and the teens are lower.
But we got to remember, it's still February, Robert. And we do live in North Dakota.
Yeah. You're not wrong. You're not wrong.
I always think that by the time we get to the end of March, then things are looking up in terms of the weather. So we only have, another 6 weeks to go?
Yeah. That's, for those of you who don't know, that's a weird thing about North Dakota springs. They can the winter can linger on and on and on, or it can just, it's gone. And that's my observations of just being here for 5 years. And it's like, yeah, they linger or they're gone.
Yeah. So you
it's
never know.
One or the other.
And the other thing is you can't predict it.
Right.
And you'll know what kind of spring you have once we get to summer.
Right.
So then you can look back on it. Yeah, it's pretty cool. Anyways, we do have a live chat feature that's running. So if you have any comments or questions that you have for us during the podcast, feel free to send them to us. The other thing, just to kind of some housekeeping chores. First of all, we do upload our podcast the next day on Spotify. Mm-hmm. So if you're ready to listen on that platform, you can do that. Also, and something that we always save near the end, and maybe if you don't watch all the way to the end, you miss it all the time. But if you do like this podcast, please give us a like, a thumbs up if you like.
Subscribe if you really like it.
Subscribe. And the other thing we always do is a disclaimer, Robert.
Disclaimer.
That's kind of fallen on you for the last...
Yeah, it has.
You want me to do it today?
These days, I'm going to throw it back on. Yeah, you do it today.
So as a disclaimer, whatever we say, Robert and I, as our own personal opinions and not necessarily the opinion of the University of North Dakota, the College of Arts and Sciences, the Department of Physics and Astrophysics that we're associated with, nor the state of North Dakota, the United States of America, North America, planet Earth, the solar system, the Milky Way, or the universe as a whole. How do you like that for a disclaimer?
Let's see, what is it, Laurentia? the local
The local group.
Yeah, local super cluster.
Just us.
Just us.
The other thing, too, at the start is we have a very special guest coming up next week.
Okay.
So I'm going to assume he's going to be here with us, so I will say his name. So it is Dr. David Livingston, also known, a.k.a., if you like, Dr. Space from the Space Show. So he's going to be with us then on February the 24th, and we're going to get into a lot of details regarding the commercialization of space. And this is a great time to kind of get into that because there's a lot of stuff going on. In fact, it's extremely hard to keep up with it all.
Oh, yeah. Oh.
I hope David does a much better job than I because you hear all these different companies and startups and things, and it's like, oh, my God, it doesn't take long before you get lost, right?
Right.
And you hear always the two main ones, of course.
And you've got all of them going, other than the big boys.
Yeah.
You got them all going up and down with their finances and everything, and it's like, holy cow.
Yeah, they come and go, and anyways, so we'll get a good rundown on all of that next week. And by the way, if you have an opportunity, please check out the Space Show, too, with Dr. David Livingston. A lot of important information on that. And he's been around for several years, so it's pretty professionally done. Okay, Robert. Big news. Talking about the space and space exploration.
We got this one.
We got a little bit of update here on the Artemis II mission. So just to kind of let people know in case you forgot what was going on or didn't pay that close of attention, we had a few weeks ago what is called a wet dress rehearsal. And wet just means that they actually physically put fuel, so there'd be liquid hydrogen in this case, and oxygen, liquid oxygen, LOX as they call it, LOX, on board the rockets. They fill it up, bottom all the way up to the top, all the different stages.
Okay.
And the idea is to check everything to make sure things are working properly. Anytime you're using plumbing, you want to make sure there's no leaks. You think of your house and you just replace the plumbing in your house. You turn on the water and check for leaks.
Yep.
Now, this is especially true with the Artemis rocket because the Artemis I, if you remember a couple years ago, that had a lot of problems with leakage, in the hydrogen and so on. And so they had to do a lot of troubleshooting to finally get it to launch. And it was a great launch. Everything seemed to work fine. There was some question, of course, on the heat shield. It was an unmanned Orion capsule that flew out around the moon and back again. And so they're going to repeat that. This time, of course, they're going to put astronauts on board, 4 of them. And you want everything to work fine. And so this dress rehearsal that they had a couple weeks ago didn't go so well. Once again, the leaks in the plumbing and the attachments from the launch pad itself to the rocket where the fuel lines are attached and so on. There were some people that were really disappointed about this because they said, well, you launched a couple of years ago and you had the same problem back then. Why didn't you fix things? And they did fix things. It's just that there were an issue with the plumbing.
Yeah.
Now there can be, and this is very sophisticated machinery, right? It's not like you're literally doing the plumbing in your house. And you're dealing with cryogenic liquids. And so these are at temperatures of what? Minus 200 and some Fahrenheit or so.
Yeah.
Right?
I mean, you can form liquid oxygen by dipping a balloon full of air in liquid nitrogen. So liquid oxygen liquefies before nitrogen does. And I've had a few incidents where I noticed this nice blue liquid in the bottom of my balloon. I was playing with liquid nitrogen, and people why are you so worried about that? And it's like, you think oxygen is bad? Put it in liquid form,
Right.
You've just concentrated all the badness about oxygen, all the fire burning, the burning and everything, bleaching and everything else. And you just concentrated it. Yeah, no.
But it's one of the best sources of oxygen for rocketry.
Absolutely. Because it's concentrated. You can put a lot of it in a smaller amount of space.
In fact, liquid oxygen, as far as I remember my history, that was used way back even in the V2 days.
Yes.
So something's been around, since the 1940s. I'm sure
it's
even you can go further back than that. Robert Goddard, and back in the 30s, and his tests that he did in New Mexico would be liquid oxygen.
Yeah.
In fact, the very first liquid-fueled rocket that he launched in Massachusetts, and then he got kicked out of the neighborhood. It's not a great place to launch rockets when you have people living there next door.
No. Yeah.
I think that was liquid oxygen too.
I think so.
It's been historically then for liquid fuel rockets the most important source of oxygen to mix with your fuel.
And like with Robert Goddard, though, the point is it was proper safety and handling, protocols. It's perfectly fine. Having it in the bottom of your balloon, that's not proper safety protocols.
Now, the interesting thing about the Artemis mission is because of the leaks, I should say plural, that they had to go back in and do some changes, re-engineer some fittings and so on. And so any of the February launch attempts we couldn't make.
We're scrubbed. Yeah.
We're scrubbed. So the astronauts were allowed to come out of quarantine. So now the earliest we can go, as you see there on the bottom of the slide, is the first week in March. No guarantee they can make that either. And of course, if not, then they'll go in April. And if not, they'll go in May. And if not, they'll go in June and so on. Safety is the number one priority, and it should be. When you're dealing with this kind of stuff. There is no rush to get to the moon, whether you're going in orbit around it or you're actually in the future landing on the moon. If things are not working properly, take the time, fix them correctly, and then go. We've had too many things happen in the past on the human space program, disasters, right, that hopefully we learned from, that they didn't need to happen.
Right.
And that's the thing here. So a couple days ago, as part of this testing, NASA did, unannounced, they didn't make a big deal about it. They did their changes. They filled up the rocket partially with liquid hydrogen, ran into some problems and had to stop the testing. So they're still doing some minor tests before they do the full wet dress rehearsal. Maybe in a week or so, we'll see how things go. And one of the things they found out was that the flow of liquid hydrogen was a lot slower than what it should have been. So they have to go in and replace a filter. They probably have got that done now. Who knows?
Okay.
But that's
I never thought about that. Yeah, the last thing you want is particulates or something like that to make a sputter in your exhaust.
Well, think of the fine machinery that's done to rocket engine parts.
Right.
I mean, like the nozzle that injects the fuel and oxidizer in the combustion chamber. If you have any kind of particulate matter that's gummed up in there, that can cause the whole thing to blow up.
Yes.
On startup, right? Not a good sign. You don't want that, obviously. So yeah, you're going to have all of this stuff. And don't forget, the filters are not like your filters you'd have in your furnace at home, where they allow a lot of stuff to pass through, even if you get the really fine mesh filters and pay the extra money for.
Yeah.
And imagine liquid hydrogen. You want to filter out anything that's in there if you can, because you're downstream. It can cause a big issue.
I never thought about that. Yeah.
So for those of you who are planning a trip, let's say for spring break in March, you may get lucky and actually see a launch or be down there at the time that it happens. So we'll see how that goes. And you don't have to be right there, even off in the distance.
Mm-hmm.
Now, the times of the launches change as we go later into the year until they become afternoon launches, daytime launches. So you won't get the spectacular sight that you would have if we would have launched this month with a nighttime launch.
Right.
But even so, I mean, you'd still be able to see the contrail from it and stuff like that. In fact, this reminds me the other day. So just, you go to different sites on YouTube, they have these live webcams.
Mm-hmm.
And there's one of them from Venice Beach,
Oh, okay.
right, LA. And I had just serendipitously, I turned on the live webcam, right? I was scrolling through looking for something to watch. And the camera itself wasn't focused on people, skateboarding or rollerblading around the area. It was focused up in the sky. And it was an object streaking across the sky with this beautiful contrail coming from it and this wake in the front. And as soon as I looked at it, I said, aha, it looks like a rocket out of Vandenberg, right?
Okay.
Probably a SpaceX launch. And they followed it for quite a while. In fact, you could see the stage separation and the part falling down as it reflected sunlight at different angles, right? It would brighten and fade and bright. And you could see it moving across, and they followed it for the longest till it really disappeared in the clouds, right? And got too far away and got too faint. And then immediately what I did is then go to one of the sort of the distributors that broadcast the SpaceX launches. And sure enough, they were 6 minutes into launch from Vandenberg.
Oh,
so
that's
then
cool.
I knew that's what it was. But just by chance,
Right.
I had turned it to that camera in Venice Beach.
But it goes to show you, people who have no idea that sort of thing is going on or anything. Oh, I just saw a UFO.
Well, you're taking the words out of my mouth here, because yesterday we have a local YouTube news program, ITV News, Neil Carlson here that reports in the local North Dakota and Minnesota area roughly. And a viewer from, I think it was Detroit Lakes, is on vacation down in the Arizona-California border area, and they sent him video of a quote-unquote, let's call it a UFO that they saw the other night. And when I looked at the video, it was the exact same thing that I saw live from Venice Beach. What they had witnessed was a SpaceX launch out of Vandenberg and thought it was a UFO.
Right.
And Neil Carlson was like, anyone can tell us what this is? And of course, all the comments were, yeah, SpaceX type of thing.
Okay.
But if you've never seen one before,
Yeah.
right,
is
and you wouldn't from here,
Right.
that it is highly unusual to see that, and it would get your attention for sure. But, But that's what it was. In fact, you don't know at the moment if it's a SpaceX launch. I had to verify that, or it could have been just never know when they test the Minuteman III at Vandenberg, and you'll get launches as well, or the military just launches a different type of rocket. But it was clearly, when you looked at it, you could tell it was a rocket. But of course, if you'd never seen them before, then.
Right.
But I just like how but it's interesting psychologically, and you could do a study on this. And you see something unusual, and you're in southern Arizona and California area. And when you look in the sky, instead of thinking, oh, it's the military doing something,
Right.
which, there's Area 51 is not that far away. We hear all about that kind of stuff, and there are lots of Air Force bases nearby. So there's stuff happening in the sky to military, I'm sure. But you immediately jump from seeing something in the sky, instead of going to something like, oh, it's a military or something, you immediately go to aliens
Right.
from another planet, right? Like that leap and possibilities is so great. It's like the space between us and the nearest star. It's just,
Yeah.
why do people want to jump to that conclusion so fast without even thinking about oh, it's probably the military, and let me check and see if anyone else reports this besides this right away to aliens. Like
Right.
something that the chance of that being aliens is so small, right? It's so tiny, yet you immediately jump to that.
Right. And again, people don't know what these things look like because it's not an everyday experience. But I agree with you. You know, it's like I'm going to cycle through what are other possible causes here on Earth before I start going, well, that's really strange.
Well, you would think you would do that.
Yeah.
I mean, if it was aliens, it's fantastic. It's kind of boring if it's the military, right? Maybe that's the reason people want to believe.
Could be.
Remember, trust no one over 30.
Right.
That's a little bit X-Files in there, you see.
Actually, it's a little bit of Planet of the Apes because Charlton Heston said that to the young ape at the end of the movie.
Maybe that's where the X-Files got it from.
Keep the flag burning, you know?
Yeah, maybe that's where the producer of the X-Files got it from. Never know.
be.
But speaking about going to the moon, here's some interesting update from China. So as we know, the Chinese program, and they stated this publicly, one of their major goals is to land on the moon in around 2030. And that's why we say, oh, it's another race to the moon. Well, the race was over back in the 60s.
Yeah, we won that one.
I don't know why we have to race again for the same thing, but
Right.
you know, the Olympics are going on. Let's race, okay? Okay. Now, so the things that happen with the Chinese program, space program, is not going to be stuff that they will release without them knowing, of course. They only release things that they want to be released. And what was released just a few days ago is the successful abort of their moon ship, essentially, from the rocket. And the rocket is the Long March 10. And
That's okay.
yeah.
Go ahead.
So
Sorry.
yeah, and so what they did is use the first stage of it, which you see there on the right side. Okay. And what you see streaking up then is already have been separated, of course, is the spacecraft, the Minju spacecraft, that ultimately can carry up to 6 to 8 ticonauts, you know, Chinese astronauts. That's quite a bit, you know, when you think about it. But the goal is the testing the hardware now. And we've had on the podcast several months ago where I think it was back in the middle of the summer where the Chinese were successfully testing their lunar lander.
Right.
Which is scary because of all the things that can delay the United States getting back to the moon is the fact that the lunar lander is not ready.
It's not ready.
And remember we talked about recently where Blue Origin even decided to stop, and I guess it's their money-making enterprise of sending up people up into space and then back down again in a few minutes. You just get above the Kármán line, right? And I don't know how much money they make per person on that, but they make some amount of money that they were told to stop doing those flights by internally and to concentrate on building the lunar lander, which they have a contract with NASA for.
Right.
So obviously they needed the engineers and the people power, if you like, to work on the lunar lander because they know we're behind in that. It's not going to be ready for 2030 the way things are going. And the second major company involved in all that, of course, is SpaceX.
Right.
And and that's the link with the Starship. That's why everybody's watching them. But Starship, how long have they been testing that for? Well over a year, a couple of years now, several years. And it doesn't seem to be getting any closer to having a vehicle that could land on the moon than we are, you know, at the beginning of this. And we're getting closer, to be fair. And there was a lot of improvements, and especially where a lot of things happen to be related to reentry. Right? Because you want to reuse the thing, and on reentry, a lot of the pieces, the fins and stuff, partially burn away. So they got to put, you know, different tiles in different places and different types of tiles. Well, you don't have to worry about that on the moon, of course.
Right.
Well, you have right, but what you have to worry about is just getting from lunar orbit and safely land on the surface of the moon, and then have it light up again and get back to lunar orbit. That's what you worry about. But they're testing everything.
And as we found out with Apollo, you got to worry about regolith blowing up as well because that gets into parts and so
all that stuff is important. So the next slide is just a photo of the first stage of the Long March 10 rocket landing on the water. So just practicing a soft touchdown. So they perfected that technology. Just remind you like the SpaceX.
So theirs lands in the water and then they just come and latch on and do it with a crane.
Yeah, and they can reuse that stage. I mean,
so instead of trying to land it on a platform, they just
Well, there's a test. They may decide to go to platform.
Okay.
It's a lot safer. It's like Starship, right?
Yeah.
Remember the last time they landed away from the platform in case they didn't land properly, the engines didn't light properly. They didn't want it smashing down and hitting the platform and doing damage to the platform, which would cost you money to fix. So they actually went vertical and hovered above the ocean. And then they went sideways and landed on the platform. And I was like, oh, is that ever some fancy engineering?
Yeah, it reminds me of an Ad Astra launch that I saw where the rocket went sideways.
Yeah.
And they blew it up because it wasn't supposed to go sideways.
Well, yeah. Well, SpaceX can make their vehicles on purpose go sideways. And it's incredible when you think about the engineering.
Because it's not like they've got attitude adjustment rockets or ailerons on a wing. They've got to feather side to side which rockets are really burning and which ones aren't, So, everybody seems to be getting in that business, right? Mm-hmm. NASA never really did that. No.
For some reason, right? They always stuck with the same kind of design, and then of course, eventually they went on into the space shuttle. But yeah, SpaceX is the company that kind of perfected all of that technology.
And even with the space shuttle, they went with a plane, essentially.
Yeah.
Instead of just bringing it down.
Well, don't forget, the idea was to launch the shuttle every 2 weeks.
Right.
That's how they sold it to Congress initially. Then you take all the launches per year and divide the cost into what it would be per pound, and that's why they got the cost down like $1,000 to $100 a pound, right? And let's do that. So they treat it like a truck. Mm-hmm. And it could land and take off at maybe even the civilian runways, major airports if it had to. And the other thing, one of the designs they made on the shuttle was a delta wing.
Yes.
And that delta wing, so you have instead of having narrow wings like some airplanes, it had a much larger surface area on the delta wings, and that actually gives them cross-range ability. So they could come in, but then they can divert a long ways away from the initial target to go land somewhere else. Like if the weather all of a sudden got bad at the Kennedy Space Center, maybe violent thunderstorms or something, that they could maybe land somewhere else, right? They had that cross range to do that, and you could land at one of the major civilian airports. Mm-hmm. So that was the idea, to make it as routine as possible.
Right.
But of course, it is rocket.
It's rockets, so it's never going to be routine.
And that's the issue, right? It never really became routine.
And there, no offense, there just weren't enough shuttles built to do that 2-week turnaround business. There needed to be, 10, 15, something like that?
Well, if you talk to some of the astronauts who did interviews, some of the astronauts who've commanded the shuttle, they said that the shuttle would never become routine unless you had 100 or 200 flights on the thing.
Okay, I can see that
too.
But, they had, 5?
The shuttles?
Yeah.
Yeah, so it would have been what? The Columbia was the first one. Then it was, not in order, then it was Discovery. Mm-hmm. Then it was the Endeavour. Then there was the Atlantis and the Challenger. So Challenger was actually number 2, Columbia, then Challenger. Then so 5 in total.
Yeah.
But don't forget, one of them wasn't supposed to be built. It was a replacement for the Challenger, because when that exploded in 86, one of the things the federal government of the United States said, okay, let's build a new shuttle.
Right.
And so they had to get the factory in, I think, Rockwell International at the time in Palmdale, California, to build a new shuttle.
Yeah.
So that they didn't have enough money initially for that. It's a replacement shuttle.
What I'm trying to get at, though, is you can't replace the tiles and prep everything, do damage repair on the engine nozzles, all this type of stuff on 4 ships to keep one going up every 2 weeks.
Well, that's it. Because, I think they discover. How do you really do this, right? You sell to Congress the most optimistic.
Right.
Really.
Yes.
Right. And I'm not just talking about the ability of, let's say, the space shuttle, but also budget-wise. Mm-hmm. Because you're scared, of course, of cancellation or not getting any money initially, and the program doesn't get off the floor, if you like. And then later on, of course, you run in the cost overruns. It's like, oh, yeah, but we spent so much money on the project up to this date, we can't stop, right? We have to cough up more money. You see how it works, right? Yeah. And there's a couple different ways you can deal with that. Number one, if you cost overrun more than a certain percent, let's make up a percentage, 10% or whatever, then the company itself pays for that, right?
Okay.
So if you contract out, if you're NASA and you say, okay, some company is going to build a lunar lander and we'll give you so much money to do it. And they said, yeah, we can do it in that amount of money, right? There's the lowest bidder to the government, as we always joke, right?
Yep.
And if they go over a certain percent, then that company has to pay for that. Why should NASA have to pay? Because you could purposely underbid your project just to get it approved, and then later on say, oh, and I know, in the back rooms of the engineers and the company are saying, well, we need, 50% more money to really do this. Right. Then you go to NASA and say, okay, we need 50% because of cost overruns. Why should NASA, in other words, why should the American people, be on the hook for that extra money?
Right. And you said you could do it for this. We expect a fully functional, safe product for that amount.
Yeah, and we'll give you some leeway. There's a cost overrun, 10 or 20%, whatever it be, but not 50 or 80% like some of these projects. Some of them way more than that, even way over 100%. Yeah. It's like, come on, right? What's going on here? Oh, it's taxpayer money. What do you worry? Well, it's taxpayer money. We're supposed to be good stewardess of that money.
Yeah.
So that's been the issue.
Yeah. So, yeah.
Now, SpaceX, like I said, they're one of the two main companies that are supposed to be building the lunar lander for the Artemis project. And Elon Musk, when he first got involved in SpaceX, I mean, he's done, millions of interviews probably on all this stuff. His goal ultimately was just go to Mars, right? Not to go to the moon.
Right.
It was Mars or bust in some sense. And he was intrigued by Mars. In fact, he often wondered, we should be sending people as soon as possible. And he's not alone. Other people have said that as well. In fact,
there's plenty of people, I've talked to plenty of them who are like, we've been to the moon. We've done that. Let others worry about the moon. We're going to Mars.
And remember, that was the attitude that Barack Obama had. In fact, when he was president of the United States, he wanted to send humans to an asteroid.
Yep.
That was the goal, not to go back to the moon. And the attitude was just what you mentioned, right? You've already been there. Why go again? Right. Type of thing. Let's do a new challenge in some sense. But going to Mars is such a big jump, even with present technology.
Yes.
And you really need a stepping off, a place.
You need an intermediate point, a loading bay, a refurbishing bay,
And people say, well, you've been there in the 60s, but we weren't really there in the 60s.
Yeah.
In the sense that we never landed. Yeah, we landed. We have proof of that, by the way. The rocks from the moon that we brought back, they are completely different chemically when you compare it to what we have on Earth. Yep. So somebody had to bring those rocks from somewhere else, right? And of course, if you look carefully, you can see the machinery left behind on the surface of the moon. You can see the tracks from the lunar rover that we had on there, the car on the moon. And then someday we'll have cameras and stuff or be there. You can actually see still the footprints, from Neil Armstrong.
We've got pictures of that from LRO.
Not of the footprints.
Oh, wow. I mean, you can see the trails.
Yeah, but at some point you're going to be able to see the footprints left behind from the 60s, right? So there's no doubt that we've been to the moon. But what I mean by we haven't really been to the moon is we didn't go there to stay.
Right. We went there.
Just to say we went there, you plant a flag and
home.
Eat your sandwich and you come home type of thing, like a picnic, right? But what I mean to go there to stay is like we have in Antarctica. We should have a scientific base on the moon. Moon Base Alpha, Space 1999. If you remember that show, right? And you can watch it on YouTube.
The nuclear waste blew them out of orbit. And
we'll be a little smarter about that in the future. But we should be on the moon with a scientific laboratory.
We should have been there a long time ago.
Analyzing stuff in situ, right? Right there. You pick up rocks, you bring it right away into the laboratory that has all the advanced equipment and analyze things right there. Right. And we get to learn how to work in these remote places like people in Antarctica, right?
We learn how to shield against radiation. We learn how to
how to get along with people, right? If you're trapped on the moon for 2 years, you want to be with people who won't go crazy and start fights and things, right?
Or if they do go crazy, you know how to deal with it.
And they're only a couple days away from Earth, so you're on the next cargo ship back to Earth, that kind of thing. Just because you have tape all wrapped around, duct taped, ignore that.
Because you are cargo now.
But yeah, that's a stepping stone on the way to Mars.
Yes.
Where it's not so easy to get back with present technology. And the same kind of thing, right? If humans don't destroy themselves, in the future we're going to have, bases on Mars as well. And a most, destination in the solar system that's able to that we're able to withstand the environment. For example, we're going to have science laboratories to start off with.
Yes.
And then that'll branch out into other stuff and eventually colonization of these objects. It's kind of a natural thing for humans to do.
Mm-hmm.
So that's going to happen. So this slide here illustrates the point that, like I said, initially SpaceX, Elon Musk, was focused on Mars. That SpaceX announced a few days ago that their focus now is going to be the moon. So that is a bit of a paradigm shift. And now, of course, long-range focus, I'm sure, is still on Mars. But it's like the moon is a stepping stone, and maybe we should go to the moon first and then on to Mars.
Absolutely.
So something has changed in the thought process, or somebody has said something to probably Elon Musk or his engineers themselves had said, we could probably advance faster with less issue regarding safety if we go to the moon and then on to Mars.
Now, I got a question about this picture.
Yeah.
If they're on the moon and launching, why do they need fins?
Well, that's because that spacecraft came from the Earth.
Oh, okay.
And then they can go back to the Earth as well.
Okay.
So this is Starship, right? This is not the vehicle. This is not like a lunar module from the 60s that was designed to be flown in space. In fact, it couldn't fly in the atmosphere of Earth at all.
Yeah.
But that's why.
Okay. I just like
the shuttle, right? The shuttle's in space. Why do you need wings on the space shuttle if you're in space?
Right. Well, the reason I question this one has to do with the fact that it's clearly the moon.
Right.
It's clearly launching from the moon.
Mm-hmm.
Now, its destination is unknown, but if it's not going back atmospheric, it doesn't need stabilizing fins.
Yeah, the thing is, you build these things on the Earth and you fly them to the moon, and then you can refuel them and on their way to Mars.
I will refrain from giving us a copyright strike. So.
Yeah, and then eventually back to the Earth again. So yeah, it's all designed to do that. And this may not be the final thing, right? I mean, this is the way we're going now, but people can change their minds on how we're going to build things and so on. Now, all of this stuff is designed to give you a real impact to space exploration in the future. Mm-hmm. But speaking about impact, there's been a bit of a talk lately on these really high energy particles that people have been detecting, and they're very, very rare. And this one is a paper that was just recently published this month, and it's on a very high energy neutrino. And in fact, the kinetic energy of this neutrino is estimated, as you see there in the title, at 220 quadrillion electron volts. Now, you might ask, what the heck is that? Well, first of all, another way of saying it is that it's 220 exa, E-X-A, electron volts, and exa, the prefix, is 10 to the power 18.
So one with 18 zeros behind it.
So in other words, 220 and then 18 zeros, because 220 of those.
Yeah.
And of course, that still doesn't really mean anything, because the unit here is electron and volt. And I looked up and said, okay, AI, give me something that's more familiar to me than electron volt. If I had 220 quadrillion electron volts, what kind of impact would that make, like in a more common object? And here's what AI said. It's equivalent to the kinetic energy that's energy of motion, of a baseball traveling at 50 miles per hour.
Yep. I was going a little faster. I was going to say it was a baseball doing 60, but yeah.
And the other interesting thing is this is not the highest energy particle we've ever detected. We've detected cosmic rays that were traveling much faster, therefore at a higher kinetic energy, and that's equivalent to an impact of a baseball traveling at about 80 miles per hour.
Right.
So you're getting to the point of the fastest that a major league pitcher can throw.
Mm-hmm.
So imagine that smacking you between the eyes. Not a good feeling.
Yeah. And I'm glad there's 90 miles of atmosphere and a magnetic field between us on these particles. Except a neutrino.
Yeah, no charge, because care less. But these particles are so tiny, so the neutrino can rip right through your body, not do any damage at all, go out the other side and keep going with a smile on its face, and you never even know that it went through you. In fact, these particles are extremely rare, and you might say, well, how do we detect it? Well, we have large area detectors. This one in particular was detected with the photomultiplier tubes that we have essentially underneath the Mediterranean.
Okay.
And they're looking for flashes of light as the neutrinos interact with known particles like electrons and so on, the Cherenkov radiation, as we call
I
it.
happened to be watching a show earlier today on neutrino detection, and they pointed out that the chances of a neutrino interacting with an atomic nucleus, which is what has to happen, passing all the way through Earth, is 1 in a billion. So, yeah, these things could be passing through you all the time, and they will do no damage because, you know, if it's 1 in a billion going through the Earth, it's, you know, an unfathomably large number for you.
So what really does this is the fact that it has no electric charge.
Yep.
So it's not going to interact with the electromagnetic force in any way.
Mm-hmm.
In fact, when we think about neutrinos, you think of radioactivity, decay,
Right.
and that involves the weak nuclear force.
And that's the problem.
And the other thing is neutrinos also have a mass, so then obviously they would react gravitationally, but their masses, and we don't know what their masses are, we just think they're very, very tiny. We know they do have a mass, and because of that, they cannot travel the speed of light. It has to be slightly less than the speed of light. But their masses are so tiny, the gravitational interaction is just extremely weak.
Yeah.
Right? Depending on what you're doing, it's essentially negligible in that sense.
It's got to get close enough to a nucleus that weak force interaction happens, and that's on the scale of about the width of an atomic
That's
nucleus.
right. It has to be a bullseye hit. Now, over cosmological distances, they do have an impact gravitationally because they have a small amount of mass. There's such a large number of them that if you add up the total mass, that actually makes up a certain fraction of the dark matter component in our universe.
Right.
Not all of it, not a huge amount, but a small amount.
Yep.
So in that sense, you could say that dark matter, at least one part of it, is neutrinos. But it's just like there's a lot more out there that's missing.
Right.
And that's the mystery, is what is the other
That's the cool
stuff.
thing. Job security, folks.
Now, for this particular paper, the question is, isn't it cool that we found a neutrino with such a large amount of kinetic energy? The problem quickly becomes, what is the origin of that particle? How could a neutrino
Have that
pick up
much
that
energy.
amount of energy? Because the electromagnetic force is not going to have anything to do with it. So how could you have a neutrino then arrive on Earth with such a large kinetic energy?
Oh, I didn't think about that. That couldn't come from a fusion process either, because that's more energy than hydrogen fusion produces.
Yes,
Holy cow,
so
that's right.
just remember that fusion reactions do produce
Neutrinos.
neutrinos. In fact, that was related to how we realize neutrinos do have mass. And that's very famous. If you go south of where we are right now, you're into South Dakota. And if you go to the western edge of the state, there is the Homestake mine. And in that mine, Raymond Davis ran an experiment trying to detect the number of electron neutrinos that were emitted from the sun. And he did that for many, 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 many years, for decades. It's very painstaking work. You count the amount of radioactive argon that's left over in your cleaning fluid in your big, huge bathtub, essentially.
Yeah.
And you have to do very detailed counting, every couple of days, and then infer from that how many neutrinos interacted with those atoms. And that would tell you roughly what is the rate of emission of neutrinos, electron neutrinos, mind you, from the sun. And why I say electron neutrinos, because as far as we know, there are 3 different types. Mm-hmm. There's one associated with the electron, as I mentioned, one with the muon, and one with the tau particle. And so we have electron, muon, and tau neutrinos. Now, given the reaction rates in the core of the sun, and someone might ask you, how do you know what actually is happening in the middle of the sun? It seems like there's no way you can peel off the layers of the sun and stick a big tube down into the center and then look at it, right, or something like that. No, what you can do is you know what is the amount of energy emitted from the sun. And how do you know that? Well, we can measure it here on Earth, for example.
Because
right?
it's in equilibrium. Because
Yeah.
it stays the same size.
And how do you know that? Well, you watched it for many, many,
Right.
over a long time period. And you don't see any change in the size that we can measure. So the thing is that we can measure the energy, the luminosity, as we say, of the sun. Okay? Measure the flux and then backtrack to what the amount of energy being emitted. And that energy is coming from nuclear reactions of hydrogen into helium.
Right.
And part of those reactions is the emission not only of light in the form of gamma rays initially, is also the neutrinos.
Right.
And if the nuclear reaction rates are occurring at a relatively slow rate, the number of emitted neutrinos would go down, right? If it all of a sudden had changed, it would be much less of these neutrinos being emitted from the sun per second. If you increase the fusion reaction rates, more neutrinos are emitted per second. And so what Raymond Davis had done was that he calculated what is the neutrino rate based on what he was detecting here on the Earth. And that neutrino rate was too low. He was only detecting 1/3 roughly of what he should have detected given the luminosity of the sun, how much energy it outputs per second. That was a real problem and a real mystery.
For a while, we were wondering, hey, is there another process involved in energizing the sun?
Well, people are thinking of all kinds of things to try to get around this issue. But from the theoretical side, what we discovered was that neutrinos could undergo what we call oscillations, which means they could actually change from one type to another. So, and initially, let's say an electron neutrino could oscillate into a state where it was really a muon neutrino or a tau neutrino. And these oscillations occur over time. The neutrinos, at the time, we thought they were massless, which means they didn't have a mass, so they would probably travel at the speed of light, but it would still take them over 8 minutes to go from the sun to the Earth. And during that time, that duration, they could oscillate from one flavor, if you like, to another. So by the time the neutrinos arrived here on Earth, all of those electron neutrinos that we thought should be produced in the nuclear reaction rates in the core of the sun, some of them had changed into other flavors. And those other flavors, the muon and the tau neutrino, they're not sensitive in the detector that Raymond Davis was using. Detector was only sensitive to the electron neutrinos. So he missed the other ones. And in fact, it turns out, and this was done through other experiments, and by the way, Raymond Davis passed away now, but he did win the Nobel Prize in Physics for this experiment. But others detected at like the Sudbury Neutrino Observatory and also the Super Kamikade neutrino detector in Japan, they were sensitive to other types of neutrinos, not just electron neutrinos. And sure enough, they discovered that those missing those missing neutrinos were actually in the form of muon and tau neutrinos, not all in the electron neutrinos.
Bottom line, the total neutrino flux matched up with.
Yes, it's just that they had oscillated into these other flavors. So this theoretical understanding of oscillation neutrinos then is actually correct. And people have won the Nobel Prize in Physics for those type of experiments as well.
And it hinges on neutrinos not being massless.
Right.
They have to have some mass.
And the thing is, from the theoretical side of things, we know more about their difference in mass from one type to another, but we don't know the absolute mass.
Right.
But what we think, and there are experiments that are being designed and being run today to try to measure that their masses is extremely tiny.
Yes.
So that's why, even though there's so many of them out there, being released from all these different stars, that they make up some fraction of the dark matter, but not all of it. But it still doesn't explain where do you get such a high kinetic energy neutrino. And there have been lots of speculation about this, and this paper speculates it might have been emitted from an exploding, what we call primordial black hole.
Which we've discussed on the show.
And the word primordial is important. Some of this was done early on. I think it was back in the 70s by Stephen Hawking and others.
Yeah.
That under the right condition, a very dense part in the early universe, that you could get, an overdense piece of matter that would collapse to actually form a black hole. Mm-hmm. And a black hole is such, and then from this perspective we're thinking of, is where space has curved in on itself. So anything within a certain distance, if you like, of the black hole can't escape to the outside universe. It's forever trapped in that bounded.
It can
curved,
only move through time. It can't move through
space it's
anymore.
Trapped inside of that closed off region. Another way, which is really not the best way to think about it, but maybe a better way to understand it if you're not familiar with all this, is you can think, the escape velocity on the surface of the black hole exceeds the speed of light, so you'd have to be traveling faster than the speed of light to get away. But that's technically not the correct explanation, but anyways, there's two ways you could think about this whole thing. Now, primordial black holes, some ideas suggest that they were formed very early on. And the interesting thing, also from Stephen Hawking, is that black holes lose mass. It's known as Hawking radiation. So black holes evaporate. For a stellar mass type of black hole, this rate of evaporation is so minute that you'd have to wait many, can I put another one in there? Many times the age of the present universe, which is about roughly 14 billion years, to be able to see some stellar mass black hole actually evaporate to nothing. But as a black hole gets smaller and smaller in terms of its mass, this rate of evaporation speeds up. So you get this kind of almost like a feedback loop in some sense, where you get a final little minute primordial black hole would go whoop, and it just blow up or evaporate, at that final moment. And so if they've been created, and we don't know, no one has ever detected a primordial black hole, so we don't know if they exist. But we look for signs of that final sort of explosive-like emission of light. And at first when we discovered gamma ray bursters, people thought maybe what we're seeing are these primordial black holes that are just evaporated away.
Right. I remember that. Yeah.
And then when people looked in detail of what is the energy that's being released from these gamma ray bursts over multiple wavelengths or energies, they discovered that it didn't fit the pattern, the spectrum, if you like, of the type of energy we think should be released from these primordial black holes, so it didn't seem to match. In fact, as we investigated things further, a lot of these gamma ray bursts are tied directly with supernova explosions, not primordial black holes. Not to say that they're not out there.
Right.
We just haven't seen any, and we're still looking. Okay? So the idea for this paper is that one of these exploding primordial black holes would have enough energy to be released in the form of neutrinos that it can explain this 220 quadrillion electron volt object that we detected, the neutrino we detected here on Earth.
Yeah, because again, something had to give it
Something
a kick.
had to give it that
hydrogen
impact.
fusion doesn't pack that much of a kick.
For sure. So at this moment, we don't know what it is. That's the thing. And is this telling us that primordial black holes do exist? In fact, some people have speculated this is a way of solving the dark matter problem, that it is in the form of primordial black holes. Other people are not so convinced. I mean, the jury's still out on that. We have to wait and see. It's interesting for sure.
It's interesting, though.
Now, speaking about black holes, another paper that came out recently is one that suggests, there doesn't have to be a supermassive black hole at the heart of the Milky Way. Now, just to show you where the evidence comes from. So for many decades, we've watched stars orbit around the center of our galaxy. I mean, in close proximity. And you can use, Kepler's third law of motion from the 1600s. If you can watch, let's say, a planet orbiting a star, and you get an idea how long it takes that planet to go around that star, and its average distance from the star itself, what we call the semi-major axis, Kepler's third law, which is really just Newton's laws, okay, tell us what is the total mass, the combined mass of the planet plus the star.
Right.
And of course, the planet's mass in general would be negligible usually compared to the mass of the star. So essentially it's a way of calculating or estimating the mass of the star, the object that would be at the focal point of its orbit, the planetary orbit.
Right.
So if you watch stars going around the center of the Milky Way, those stars travel pretty rapidly when they're nearest to the object that's at the center of our galaxy. And over time, we have estimated using Kepler's third law, basically, that mass that's at the very center is on the order of 4 million times the mass of our sun. And yet, when we look there with all our different telescopes, we see nothing.
Right.
So, Robert.
And we know about how large it has to be. So that 4 million solar masses has to be in a compact region of space. It can't be just spread out.
No, we looked at very high resolution imaging. We thought that it might be just like a star cluster containing a huge number of stars. Altogether, its mass, be at the 4 million. But when you look there, you essentially don't see anything. So, Robert, what would have a mass of 4 million times the mass of our own sun
Right.
And by the way, for those who don't know, that's about 2 times 10 to the 30 kilograms.
Yeah.
One solar mass. So you multiply that by 4 million. That's in a relatively very small volume of space.
I'm going to call that a black hole because that's the only thing.
And there's nothing there. You can't
known.
see anything.
Yeah.
Now, a couple of years ago, back in 2018, the Event Horizon Telescope actually took an image of the black hole that's at the center of our galaxy. Saw the shadow of the black hole.
Yeah.
So we thought everything was like hunky-dory, right? It's, the case is closed. There are black holes. And in fact, we've taken an image of the shadow of them. And there was one in our galaxy and in another galaxy as well. Case closed. But this paper is suggesting not so fast. There is another explanation. And this other explanation involves what we call fermionic dark matter. Now, you might wonder, what the heck is fermionic dark matter?
I'm wondering what the heck that is.
Fermionic dark matter. So dark matter can be in various forms. If you don't know what it is, you can speculate till the cows come home.
Right.
As long as you satisfy certain observational constraints, of course. Fermionic dark matter will be dark matter that obeys the Fermi-Dirac statistics. Now, you remember your chemistry and your physics, that Pauli exclusion principle.
Right.
That applies to
Leptons?
leptons, which are fermions. They obey the Fermi-Dirac statistics. So fermions. The other one is the Einstein, the Bose-Einstein statistics. So you're talking about bosons. And bosons can occupy the same region of space. You can think of it that way.
Right.
Where fermions can't, right? They can't have the same quantum numbers and stuff. If you get into quantum mechanics, you learn all the more technical.
You learn all this.
The more technical way of describing, which I don't want to get into right now in the podcast here. So it's fermionic dark matter. That fermionic, because they can't collapse to zero, because they can't occupy, but they can collapse down to a very highly compressed region. In fact, collapse enough so that it can explain the orbital motion of the stars that's in orbit around, quote unquote, the black hole at the center of the Milky Way. Now, to show that, of course, you have to have some observational evidence of that.
Or else people are going to discount it and not publish your
Yeah,
paper.
or you got to do some other, got to get involved in some detailed observations that you're going to make in the future to prove or refute your claim. Now, what we see here is a rotation curve. Now, rotation curve, as you see on the vertical axis, is just how fast something is moving. So it's a speed, kilometers per second is the units in this case. On the horizontal axis on the bottom is just distance from the center of the galaxy. And these are units, a lot of times it would be in, you could have it in light years, for example. In this case, it's in parsecs. Now, 1 parsec, just for conversion here, is 3.26 light years. Okay. Now, notice that if you go to the left side of the bottom, that you're really close to the center of our galaxy. You're right in there, a really small amount of parsecs. In fact, you're getting into where the black hole region exists, the event horizon of the black hole.
Hence that little bump at the top.
Right, and so
drops back.
Yeah, well, if you're at the very center, what is your speed orbiting the center? 0, right?
0.
Because you're at the center, you see? And as you come out, your speed picks up, right? Now, the traditional sort of rotation curve that we know and love of the Milky Way is the one you see in the yellow dots, sort of on the right side of the plot. And if you look carefully, there's both a disk component, a bulge component, and it's sort of an inner bulge component. And then fitting all the data is the Milky Way. That's the solid bluish line on the very top of the key legend that's there. And what you see here there are 2 data points. There's one that's sort of more of a reddish color. It's labeled S2. And there's another one labeled G2. So these are objects that are orbiting very close to the center of our galaxy, where they're under the direct influence of, you would say, the gravitational force of the black hole, or if you like, they're in that highly curved space-time around the center of at the very center of our Milky Way. And there are models that we use to fit their orbital motion. And notice that the model for the inner bulge area goes, or for the fermionic dark matter, the second one down from the top, where it says Milky Way, MW, the DM is dark matter. And this is for fermionic dark matter, that part of the rotation curve, right on the inside of it, if you like, near the very center, is well fit by assuming fermionic dark matter. The data points lie right on the line. Now, is this a case closed? No, because if you were to plot the same type of rotation curve for assuming that there's a 4 million solar mass black hole at the center of Milky Way,
You get the same fit.
you get the same fit. They differ by less than 1%.
Oh, okay. Yeah.
So you can't discriminate the two models. But it's interesting to know that here comes another model that doesn't rely on the existence of a supermassive black hole, that has these properties of this fermionic dark matter. And you can essentially, at least for these two data points, reproduce the rotation curve that you need and be just as well off as the one for the supermassive black hole. Interesting when you think about it.
Yeah, but how does gravity not crunch it? Because dark matter is still affected by
Fermions,
gravity.
they can't occupy the same space.
Except I want to know what produces that
Right.
pressure. I mean, we know what it is with electrons. We know what it is with the other fermions. Why is this still not collapsing under gravity? You know, electrons are fermions, and yet they collapse at those densities. So, yeah, I'm like, I want to see more.
Now, some good news, sort of an update. This is the world's largest optical telescope that European Southern Observatory is building, and they released an image a few days back, so I thought I'd share this with everyone. Getting really close. Now, first flight is scheduled for 2029 still, so still 3 years away. And this will be the largest optical telescope, as I mentioned, a 39-meter equivalent diameter
That's crazy.
telescope.
That
Our
is
largest
crazy.
ones out there now are about on the order of 10 or so. And depend how you count it, 11 if you count the large binocular telescope. But so you're on your 10-meter class telescopes, and we're jumping to essentially a 40-meter diameter
Yeah, but
telescope.
the thing is it scales as a square value,
Yes.
an inverse square value. So you've got to make that kind of jump at this point to get any.
Well,
improvement.
the light gathering ability goes like the area, which is the diameter squared.
Right.
So this is going to be a huge increase in light gathering ability. And along with that, much higher resolution, especially you're going to use adaptive optics to try to compensate for the Earth's atmosphere. And the next slide gives you kind of a view from a little bit far away, looking at the peak down. And by the way, it's located down in Chile. And so down in the Andes Mountains. So you have very good skies, of course, nice and dark, especially since the plan, as we mentioned a few podcasts ago, to build an industrial park nearby and ruin the night sky for this telescope. Those plans have changed, so it will not be put there. Thank
goodness.
everybody who made a big deal over it.
Yeah.
Now, for those of you who've seen our podcast last week, where we talked to Dr. Simmons about early life, one of the things we mentioned about the discovery of amino acids on the asteroid Bennu, and you know what new paper just came out about that serendipitously, which is interesting, and it once again studies the amino acids that were found on the asteroid Bennu, which is an asteroid that we actually went to, grabbed up some of the material and brought it here on Earth, so you can do detailed analysis on our laboratories. Is that they discovered that these amino acids seem to be formed differently than what we had seen in the past. Now, Robert, if you go to the next slide. So back in 1969, this meteorite was discovered in Australia, the Murchison meteorite. And when they analyzed it in detail, they found over 60 different types of amino acids in that meteorite. So that's
kinda
the
crazy.
one I think Becky
Yeah.
was mentioning, right?
Right.
But for the asteroid, and those amino acids on that meteorite, there was evidence that they formed in a warm environment in which you had, of course, liquid water available to form. And of course, when you're studying a sample of one, you think that that's the only way you can form this stuff somewhere in space. But it turns out that the material from asteroid Bennu, it seemed like those amino acids were actually formed in an icy environment, that they weren't formed in a warm environment in which H2O would be in a liquid form.
That's kind of crazy.
So they're suggesting that there's actually several different ways of forming amino acids. They're not all the same.
I will point out, because I made the same mistake until just a second ago, that little symbol like in green behind the 7 is not a percent symbol. That's what we call a mill symbol. And it means part per 1,000, not
Right.
part per 100.
Right.
So, yeah, these are all talking in PPT, parts per 1,000. Wow.
Yeah. And speaking about that, and this, talking about life on other planets, a recent study also showed that, for life to arrive on exoplanets other than the Earth, you really need nitrogen and phosphorus.
Yes.
That's some of the like basic ingredients.
I mean, we evolved out of needing phosphorus, but you really do kind of need that energy kick from it.
that initial beginning
Yeah.
of life, right? And what was discovered was, in a lot of these planets, the concentration of nitrogen and phosphorus is not always there in the amounts that we think would be conducive for the formation of life. In fact, there's sort of a sweet spot, a Goldilocks zone, where you have some of these exoplanets that have been detected. Most of them don't fall in that sweet spot.
Interesting.
So here's the plot showing you the ratio of what you have phosphorus in the mantle compared to what the Earth has in the mantle. That's the vertical axis. The horizontal axis is the ratio of what we suspect to have in these exoplanets of nitrogen in the mantle versus what we have in the Earth.
And if I can inject here, if you're looking at this graph and you can't make any sense of it, don't worry. I can sit here, I make sense of it, and I can tell you it'd probably take me an entire podcast to explain what is going on in this one graph. So don't feel bad if you're looking at it going, huh?
So having the right amount of concentration of both nitrogen and phosphorus that leach up from down below of the planet that you're on is very important in order to support the formation of early life.
Right.
And those conditions, as far as we know, are not always there.
Yeah. And to put it in perspective, the reason I made the comment at the start of this conversation about needing phosphorus to get things going, if you remember from your high school biology, what powers our cells is ATP. That P at the end is phosphate,
Right.
a phosphorus-bearing ion. So phosphorus is a highly energetic atom, and it forms a lot of highly energetic ions. And so you need a certain amount of phosphorus for our type of life. And in fact, when you're talking about anaerobic life, you need a lot more of it because those processes produce a lot less ATP and so forth. At least if I'm remembering my biology right.
Right. Well, it's certainly interesting. Could have a major impact on early life somewhere else and other planets around other stars. So it's definitely something to consider. It's not just where water is in liquid form.
Oh, yeah. No.
Right. There are a lot more other things that are involved as well. But if you're interested in all this kind of stuff, one of the things you can do, of course, is to advance your education. Go to, if you're in high school, let's say, go off to university, go to college, go learn, higher educational type of programs. Come to the University of North Dakota.
Absolutely.
For example, we have lots of programs, both online and on campus, to hopefully something fits your excitement and your niche, if you like, including biology.
Including biology.
Including physics.
Yep.
Including mathematics. Including all the major STEM sort of departments that you would think about at higher education.
Let's just call it STEAM because
and the arts as well. Exactly. I mean, one of the things you have to do as a scientist is you have to communicate to other people.
Right.
And
Which means you need these pretty pictures and other things.
And you got to be able to write.
Oh, yeah, you got to be able to write.
So it's extremely important to do all that. Plus, you want to describe things to others to get people interested or to appreciate what things you're looking at and why, all these kind of things. So higher education, the way to go. UND is a perfect place to come to. Now, our next podcast, as we mentioned at the beginning today, is on next Tuesday, February 24th. We will have Dr. Space, Dr. David Livingston, who will be our special guest. So that'll be very interesting. So hopefully you can tune into that when we actually do the podcast so you can send us questions. Remember, that's always at 5 p.m. Central Time.
And you know what? Go give his show a listen, a watch.
Yeah, that's the space show. So that's been on for quite a while, and he has lots of really good guests on that show. So it's definitely a place to go and get more, if you like, of this kind of talk like we did
Always
today.
come back to see us. But check him out before.
As soon as you're done with this podcast, go check out his stuff.
Yeah.
The other thing is we always leave you with a quote or an excerpt at the end of our podcast. So today I decided to choose an excerpt from the paper that announced the first discovery of planets around another star.
Oh, this will be fun.
And this was in 1992. And it's the title of the paper is A Planetary System Around the Millisecond Pulsar, PSR 1257 plus 12, by Alexander Volshin and Dale Frail, who is also Canadian, by the way. I got to put that little plug in there. Here's kind of a summary, if you like, of what they discovered. So, by the way, this was, like I said, the first time we discovered planets convincingly, because there was some evidence and then it kind of went away. It was the first time we discovered planets orbiting other stars. So here's what they said. The detection of a planetary system around a nearby, approximately 500 parsec, old neutron star, together with the recent report on a planetary companion to the pulsar 1829-10, raises the tantalizing possibility that a non-negligible fraction of neutron stars observable as radio pulsars may be orbited by planet-like bodies.
I still have questions about planets around pulsars.
Now that seems a really hostile environment for planets to form. They must have, you would think, have assembled after the supernova explosion that created the neutron star.
But if they assembled after the supernova, how did they form so fast?
Or somehow migrated inwards after the event?
Yep.
So I looked it up. So it's been a few years since 1992, of course. How right or wrong is this excerpt? So they're saying that there's a non-negligible fraction around neutron stars. So people have looked and looked and looked. Yeah. In fact, the number of planets that have been confirmed to be around neutron stars on the order of 5 to 6.
Wow.
And there's like at least 3,000, if not more, pulsars that we've cataloged up to this point.
Which
means that only a very, very small number of neutron stars have planets. So these gentlemen were extremely lucky in their observation to detect this.
Probably has something to do with being an old, therefore slow rotating pulsar too. But
could be. It's very interesting planetary formation. Now, if you like this podcast, like we said earlier, please give us a thumbs up. Please subscribe if you haven't subscribed. And thank you very much for listening.
You have a good night, folks.